Today, let's look at secants, tangents, and finding limits with tables. And just to start with, let's review a little bit from the last class. Here, this is saying fill in some tables with x values that limit to infinity. So on the number line, infinity is this guy on the right here, and there was 0 and 1. And so we want x values to get closer and closer to infinity. You have to start with 1. And since we're humans, I always say start with 10, because we have 10 fingers, decimal-based system. And then to get closer to infinity, I know you could write 11, 12, but that's not good. We need to get closer to infinity faster. So you say 10 times 10 is 100, and I just add another digit. And the reason is because as we use these values later on, we'll want to try to get some kind of convergence that gives us a digit of convergence each time we plug in a new number. So you see these are getting closer by bounds to infinity. And the next one would be 10,000, right? Just times 10 again. Minus infinity is on this other side. So we would start with minus 10, and then minus 100. So those are getting huger negative numbers, at least in magnitude, and so they're getting closer and closer to minus infinity. And then we looked at regular numbers, like if 5 from the right side. So if you had 5, we'd be interested in the plus and the minus side. We're interested in going towards 5 from the right, like that. And what I said was, well, first just take that 5 plus. If you're not sure how to start, you just write that above each of these cells that we're interested in. And then I said use a dollar, a dime, which is 0.1, and a penny, which is 0.01. And then just treat that plus like an addition. 5 plus 1, 6. 5 plus 0.1, 5.1, 5.01. And those are getting closer and closer to 5. You can also go to 5 from the left side, in which case, so we'd be kind of on the left side here, going towards 5. So I would just write the 5 minus each time. Whatever's here, I just write up here. And then put the dollar, the dime, and the penny. And you can see I'm getting one more digit each time. So 5 minus 1 is 4, 4.9, and 4.99. $5 minus a penny. So those are getting closer and closer to 5. You can also have minus 5 from the right side. So on our number line, if you had minus 5, and you may not have the cycles in your mind on a test to really think about it a whole lot, but the right side and the left side of minus 5 is kind of backwards. So if we're talking about the right side, it gets a little confusing. We want minus 4 to start with. So what I do is I just write it and use this trick if I ever get confused. Minus 5 plus, minus 5 plus, and then just do the dollar, the dime, and the penny. And then minus 5 plus 1, put it in the calculator, minus 4. Minus 5 plus 0.1, minus 4.9. And it'll set you straight if you're getting a little backwards. Those are getting closer and closer to minus 5. And then 0 from the left side. Again, just copy those guys. 0 is a little bit special. So, but the trick always works. So minus 1, minus 0.1, and minus 0.01 are definitely getting closer and closer to 0. That's just an arrow. And then working in some of this algebra review while we get started here. I'm going to zoom in a little bit. So here we have a function, f of x equals 3x squared plus x minus 5. Whatever x value we get in here, we plug in for the x there. So here we have 3. It would, where the x was, I'll put parentheses. And then I put 3 in. And then we just have to be a little careful. First square the 3, then times the 3. So it's 3 times, that's 9, plus 3 minus 5, and so 27 plus 3 minus 5. And so I just picked 2, I got 30 there, and then 30 minus 5 is 25. Let's try f of 3 plus 5. Well, in this case, you have 3 plus 5 in parentheses, so I'll just write f of 8. Go ahead and add those guys. So 3 times 8 squared plus 8 minus 5. So again, we just square the 8 first. 3 times 64 plus 8 minus 5. So what is that? 180 plus 12? 192 plus 8 minus 5. And again, pick 2 of them. You got 200. Now 200 minus 5, 195. Sounds about right. And then f of 8, we just did it. So 3x squared plus x minus 5. Then on the next page, there's a couple more here. Unfortunate page turn there. So 3x squared plus x minus 5. We'll plug into a. So we don't have a number this time, we just have a. So wherever the x is, we put the a. So 3a squared plus a minus 5. That was easy, right? And then now we have a plus h, and we can't really combine them, so we just wherever the x was, I'll put the a plus h in parentheses. And so this is squared. So a plus h squared, you could use FOIL if you know how to do that one, because it's a plus h times a plus h. And then it's first, outer, inner, last. I'm going to use something called the box method, where you put the a and the h twice, because it's a plus h times a plus h. And the reason is because this scales well if you have more terms. So now you have four things that are going to come out of this square, just like FOIL. So look at the column and row headers. So for this box, the column header is a and the row header is a. So a times a squared. This one, it's a and h that line up with it, so ah. And then this one, h and a, I'm going to write that as ah. And then two h's. So we have a squared plus ah plus plus h squared, which is a squared plus 2ah plus h squared. So then down here, we have 3 times a squared plus 2ah plus h squared plus a plus h, no need for those parentheses, minus 5. And then we multiply the 3, like super distribute that guy to each term. So 3 times a, 3a squared, plus 3 times 2ah, 6ah, plus 3 times h squared, 3h squared, plus a plus h minus 5. None of those are like terms. It's a squared, there's no other a squared. There's a times h, there's no other a times h. So all those are unique terms. If you're having some trouble with that, you might want to do a quick algebra review, or ask me if I have something that I can send you, and we also have online tutors. So consider this problem. Give an arbitrary function f of x and a point on the graph. Find the slope of the line tangent to f at that point. So let's just look at a couple things. Like if you have a circle, we can look at a secant of the circle. That's where you slice it. It's kind of like slicing a piece off a cheese wheel. That's a secant line. And that's not a function. It's a circle. But this is a function. You could have a cubic. And we'll talk about why it's a function later on. But you could have, you could also take a slice off of that. You see how it doesn't meet at a point? It hits 2 places there, just like this one did. And even though it's going to hit it again down here, what we call locally, or in this little area, it slices it. But you can also think of this as, well, it's not the best drawing, but if it hits, it just kisses it at that point. You think this is like a 2x4 against a, I don't know, a telephone pole or something. It'll hit it just one point if it's a straight 2x4. And that's called the tangent. And then also on our function, you can select a point and you can draw a tangent at that point. That's where it hits it. It's just one point. And the bottom line, it's a secant slices, a tangent just touches. So we can draw tangent lines for the following. You might want to pause it and just draw to make sure you've got this, you're seeing it, but there's a tangent line. This one's really weird. It kind of goes really close, but it slices through. And that one's a tangent. And here's one. It's just like kind of like you're going to shave off a mole there or something with somebody's face. And then here's one. It's a little steeper, but should only hit at one point. And then this guy here is a challenge of my stylus skills. If it's on a line already, then the tangent line is the line itself. And then here's one where you can see like the octopus function, or here sine, or that looks to be cosine. So here you can see it's gonna punch through that guy later on too. But right here in this area, it's tangent. If you zoom in enough. All right, so y equals x squared, or f of x equals x squared. That's a function you should be familiar with. It looks kind of like this. It's a smile. It goes through 0, 0, and 1, 1. And let's say that we're interested in x naught, y naught, 0, 0. So we're interested in this point right here. What's the slope of the tangent line? Well, if you draw the tangent line there, you can see it's the tangent line is horizontal. So the slope of a horizontal line is 0. It doesn't go up or down. It doesn't rise or go down. It doesn't incline or decline. It's just flat. It's a constant function. So what about at 1, 1? So here you can see, there you can draw it. but it's not so easy. It happens to be, I believe, 1, but not so easy. This is what we're trying to figure out. So yeah, generally speaking, you can, with 2 points, you can figure out the rise over run over a line. But with just 1 point, you can't. So if you have your function here, and you've got a secant line, you have 2 points, and you can do this little gem that you may remember for the equation of the slope. But if you have this guy, it's just kissing it, you only have 1 point. So what's the slope of that guy? It's hard. It's a tangent case. But the thing that's interesting is as the secant lines get closer and closer to the point, the slope of the secant gets closer and closer. So basically, if this is our point, well, let me draw it another way. If we have this is our point, we can select other points that get closer and closer to the point. As we do so, the slopes of these guys get closer and closer to the slope of the tangent. You see how that's way off, but these are getting closer and closer, and if you drew another one in, it would have to go between both these lines each time you get closer and closer points. And that's the essence of calculus right there, or at least derivative calculus. We're looking at how these secant lines get closer and closer to a tangent line. How do we get the slope at 1 point? You use a bunch of 2 points to get there. And a lot of the time we'll spend will be on figuring out for complicated expressions what the slope of that tangent line is. And then it just pops up everywhere in applications. So we'll look at lots of applications in this course. And so let's look at the limit. First of all, I think I told you the pillars of calculus. We have the limit and continuity, and on that rests calculus. And calculus, you might do a derivative and something we call the antiderivative, or the integral, or the main pieces of it. So functions, so limits. Let's think about functions. If you have a function or any relationship between 2 variables, you can have a rule, a chart, and a graph. Those are 3 different ways to represent it. So you might have y equals x squared. You might make a little table with x and y and put some in there, right? So 3, so 1, 4, 9. And then from that, you could maybe, say we use the rule to fill that in, and then maybe draw the graph, which in this case is y equals x squared. So each one of these you can go to the other way. Similarly, if you have a graph, you might draw the chart, or at least take some of these points for a chart, and then from that try to figure out the rule and go the other way. And so you can kind of see that we want to connect this. And basically K through 12, we spend a lot of time going from the rule to the chart to the graph. And so that's what I just did right there. Okay, and just another thing, if you see f of x, that's the same thing as y. So if you see f of x equals x squared, we often just use another variable. Same thing. But let's say if we're interested in finding the function's value at 1, in this case you can just plug that in. You can say, oh, f of 1 is 1 squared. So, oh, that's just 1. So we know that 1 comma 1 is on the graph by using the rule and just plugging it in. But what if you couldn't? Let's just try a little game here. Like, you can plug anything you want, but not 1. How would you find f of 1? And you know it's, in this case, a continuous function. Kind of skipping over that, but you could try things larger than 1. So you could look at the limit as x goes to 1 from the right side, things larger. And you could try things smaller than 1. Take x things that go to 1 from the left side. So on the number line, if there's 1, we can try from the right side and from the left side and see what the values are. So maybe they go like this. There's our key value that we can't plug in, something like that. And maybe they both get close to it, and that should tell us the y. So in this case, here's some x values that are getting closer and closer to 1 from the right, and these are some x values that are getting closer and closer to 1 from the left. You can see we did like the 1 plus 1, that's the dollar, dime, penny, and a couple more. And here's the 1 minus 1, 1 minus dime, penny, and a few more. So if you plug 2 in, and we're looking at, in this case, y equals x squared, you could say 2 squared is 4. 1.1 squared is 1.21. 1.01 squared, it's calculator time here, 1.0201. And then the fun part of this is sometimes you see crazy patterns you never thought about. So 1.002. Do you see the pattern? The next one, without even the calculator, you see there's going to be 3 zeros. And these are getting closer and closer to, so just look at the digits here. There's 1.2, 1.02. There are the O's again. There's the O's and another 0. So it's getting closer and closer to 1 here. And then similarly here, 1 minus 1 is 0. 1 minus 0.1 is 0.9. So 0.9, I'm sorry. 0 squared is 0. 0.9 squared is 0.81. 0.99 squared. We're plugging them into the function. 0.9801. And then 0.999 squared. It's 0.999 times 0.999. It's 0.998001. You might see a pattern in there. And this one's 0.9998000. I bet you see the pattern now. But regardless of the pattern, you can see that we're getting, there's 1 9, there's 2 9s, there's 3 9s. This is 98 hundredths, 99 100ths, 999 ten thousandths. So these are getting closer and closer to 1 as well, if you think about it. They're very close to 1. And that's how we find the limit of the y terms. So here we're plugging in. So this is x squared. I just squared each of these ones in the top, just like you would do this with a x and a y, and you have 2, 1.1, 1.01. You would square them. We did that, and then we said, oh, this is going to, if you like it drawn this way, these are going to 1, and these are also just happen to go to 1, and that's what we're interested in. There's a reason I'm drawing it this way, you'll see in a few minutes. So things larger than 1 is written like this, the limit as x goes to 1 from the right of the y's. And the thing smaller than 1 is the limit as x goes to 1 from the left, or at least in this case there's a little negative minus sign there, of the y's, or f of x. And if these two are the same, that's a vertical equal sign. If those are the same, then the limit exists. And if the limit exists, then, so if they're the same, we say then the f has a limit at 1, where the x is 1. And so let's try finding a limit like you would do on a quiz or a test problem. It's a very important skill here. So we're interested in 2, and I'm interested in the limit as x goes to 2 from the right, and the limit as x goes to 2 from the left. I'm going to make my little table. And 3 should be enough. So we can do again, we can do the 2 plus each time. Dollar, dime, penny. So we have 3, 2.1, 2.01. And then we just plug it in. So what is 1 over x minus 2 if x is 3? 1 over 3 minus 2 is 1 over 1, which is 1, so that's 1. How about 2.1? That's 1 over 2.1 minus 2. See how I'm plugging in the x value into this. So that's 1 over 0.1, which is 10. And then 2.01, so 1 over 2.01 minus 2 is 1 over 0.01, so 100. This is how many pennies are in $1. So obviously the top ones were getting closer and closer to 2. But what are these bottom ones getting closer and closer to? You can see 1, 10, 100. The next one probably 1,000. They're going to infinity. They're getting larger and larger. And then same thing here from the left side. You could do the 2 minus. And 1, a dollar, dime, penny. So then you get the 1, 1.9, 1.99. See this coming from the left side. And plug those in. So what is it? 1 over, we're plugging in 1. So 1 minus 2. 1 over minus 1. So that's minus 1. 1 over 1.9 minus 2 is 1 over minus 0.1. So there's a minus 10. So you kind of see. And if you do the last one, you get minus 100. So again, these top ones are going closer and closer to 2 by our design. And then we look at the bottom and say, oh, those are not converging. They're getting larger in magnitude. It's like you're going into debt. It's bad gambling. So minus infinity there. And so we would say, then now you compare these two. And you say they're not the same. So we say the limit does not exist. And if you looked at the graph of that guy, if you plotted it at 2, it's an interesting point. It does something like, let's see here. This, it goes up asymptotically there, and then it does something like that asymptotically on the other side of that too. So there's a problem at x equals 2 finding the y value. And you can also look at this guy and say, oh, I can't plug 2 in. That's not going to work. So let's try this one now. 1 over x squared for x going to 0. So we draw our little tables. This technique always works for finding limits. All right, so here we're going to find the limit as x goes to 0. And we're interested in the right side. And here we're going to do the limit as x goes to 0. We're going to go from the other side, the left side. You can have them reversed. It's, as you know, it could be from left and right, but I'm just always going to try to be consistent here. So 0 plus a dollar, 0 plus a dime, 0 plus a penny. So 1, 0.1, and 0.01. So now we're 1 over x squared. So 1 over, plug in 1 squared, that's just 1. 1 over 0.1 squared. 1 over 0.1 squared is 1 over 100th. So it's 100. And then if you try this one, you get 10,000. You can see it's really getting big fast here. So these are getting closer and closer to 0, and these are getting closer and closer to, again, infinity in this case. Doesn't look good, does it? And then 0 from the left side, minus 1, minus 0.1, minus 0.01. But in this case, if you do 1 over minus 1 squared, you can see that squarings can get rid of the minus. So we just have a 1. And then again, you'll have a 100 there. It'll be positive. So again, these on the top going to 0 by our design. These on the bottom, if you look at them, they're getting huge and they're all positive. So it's again going to infinity. But in this case, we have, now let's compare our two y's. We have infinity and infinity, so it's the same. It's not infinity and negative infinity. So in this case, it's infinity, but does the limit exist? We'd say technically a limit doesn't exist, but I like to just note that it is infinity is the answer I'm looking for. And the graph of this guy looks like something like this. So you can see that it'll never, you can't plug in 0 obviously, but these guys are just out of control, but they are going to the same place. And then one more here, x goes to 1 of h of x, so we have x, and you can see I just put y in so I don't have to worry about f's and g's and h's. They keep changing. All right, let's try a little more complicated one here. So we're going to do the limits, and x is going to 1, and from the right, and then from the left, and see if they're the same. So let's plug 1 in. We have 1 squared minus 1 over 1 minus 1, which is, oh, it's awful. Doesn't work, right? So we can't just plug it in, obviously. So we'll need 1 plus. You can see why we might need to do a limit there. Dollar, dime, and a penny. So 2, 1.1, 1.01. So let's try plugging 2 in. So 2 squared minus 2 over 2 minus 1. That's 2 over 1. So 2. 1.1, plug that in. So room on the bottom here, fortunately. Let's try 1.1. So 1.1 squared minus 1.1 over 1.1 minus... You can see we plug it in a lot here. So that's 1.21 minus over, and that's going to be just 0.1. So we have there 0.11 over 0.1. So 1.1. And if you plug these other ones in, you'll see that you'll get the same thing. And the same thing here, we have 1 minus a dollar, 1 minus a dime, and 1 minus a penny. So 0, 0.9, and 0.99. If you plug those in and do the logic, you should get the same numbers again. So the x values are getting closer and closer to 1. In this case, the y values are the same, so they're also getting closer and closer to 1. That's interesting. And then same thing here. I didn't plug them all in, obviously, but that's a little algebra exercise. So here, are they the same number? Yeah, 1 is the same as 1, so the limit exists. And you can see you couldn't plug 1 in, but they do both get closer and closer, converge to, or limit to 1 from either side. And some of you are good with algebra. You'd say, oh, you know, the thing is, Parrish, if you look on this guy and factor an x out of the top, you can see something happens there. That's a little, but it's a little, leads you in the wrong direction, because even though it's correct, then that's fine. Now you can do all this. Just remember, you can't, if this was a computer program, you still can't plug in 1, because it'll break right there, even though it is essentially the same. In the graph of that guy, what's happening is that 1 here, we have a hole. The graph looks fine, but we have a hole there. So what you want to do, if let's say you got a computer program that was driving your new Tesla or something, and it was doing something like this, and this was the function it was using, you would have that computer program first look for 1. And if x was 1, it wouldn't plug it in. It would just say, all right, the output's going to be 1. You would have the output be 1, just automatically. It looks at the input, and then if it's not 1, it would calculate this each time. All right, that's the end of the lesson.